Welcome again, ladies and gentlemen. And a big more welcome for the people who stayed with us the whole morning while we were struggling with Ntate Bulani's presentation. So Ntate Bulani will be the last person to present today, just in case his presentation has problems again. I don't want to have a heart attack now, immediately after lunch. So the procedure is the same as in the morning. The presenter will talk, and at 9 minutes, he talks for 10 minutes. At 9 minutes, the alarm will go off, signifying that there's only 1 minute left. And when that happens, then the speaker is supposed to go to concluding remarks. So please write all your questions in the chat room so that we address them quickly. So the questions are still 5 minutes. So Ntate Moholo, please begin.
Thank you. Good afternoon. I'll be presenting to you evaluation and optimization of solar PV water pumping systems for Lesotho. I'm supervised by Engineer Hove. So the motivation of the study is that we have energy systems that are supposed to deliver a required amount of water to point of source to the user. But we meet the problem with these PV systems because of their high initial costs, lack of awareness due to lack of expertise, hence they are not properly sized, and also the lack of predictability. So the aim of this study is to model and size these systems in a comprehensive manner to attain the least cost of pumping and thus predict the water output. And we apply the Hove and Mogomba model, which considers the head flow relation and derives the power functions, which shows the time step relation of electricity to water relation. So this paper will be useful for researchers and manufacturers as well. That is our schema of photovoltaic system. It consists of PV modules, power conditioning, which has a variable frequency, which can go in synchronization with your available solar radiation, and the MPPT to ensure that the energy step is available, the energy is in step with the available radiation. Therefore, for long-term performance of these systems, it is required that you model, you have a proper analysis of your solar radiation and temperature for long-term performance, as these are sensitive to, as these are functions of the PV. So the study first of all did the methodology of developing 0.253 database of longitude across the country. And this interpolation was then, this radiation data was then interpolated so that it could match the in-between values to be read. As you can see, the temperature interpolation there with -2 at a case study that we are doing now at Quthing at that latitude with the required amount of water of 350, with the pumping main distance of 3,000, as you can see as the preliminary site information. So the first thing is to select the pump. The selection of the pump depends on the available solar radiation at the site and also the daily water demand. So we went through the Lorentz PartnerNet and we came up with this empirical data that we have to analyze. This characteristics curve shows the variation of Q in response to PV output, but with constant head, and this constant head is not realistic as the head will vary as the flow rate increases due to frictional losses. So to do this, we have to find the HQ relation, which can be found by matching the corresponding PV to the output. And we came up with this chart that you can see of HQ relations, which can be analyzed by that equation, which is nonlinear. And this are done by best fitting curve in relating the HQ relation. The system coefficients can also be found. The system resistant coefficients can also be found by plotting the best fitting curve to analyze the H1 and the H2, so that you can find the TDH at operating points. And this can be done by simultaneous equations, as you can see, or you can superimpose the two past charts together to find the operating points as the intersections of these two graphs. Where they intersect are the operating points. And therefore, our TDH op is our operating head, which varies along the day from morning hours to it becomes higher during the midday hours as the sunshine, the solar radiation is maximum. So these are, and finally we come to our relation of how the PV relate to the flow rate. As it can be seen, that it is a logarithmic by nature, and also it is parametric to our pipes. As you can see, the 125 millimeter pipe differ from 200 millimeter pipe. So once you insert your PV amount, you will know automatically the flow rate that you will attain. So from there, inputting this into the Hove model, we came up with this analysis where you can see the TDH matching with the flow rate from the morning hours up to the sunset hours. As you can see that the flow rate is maximum at during midday hours, and the sunshine is higher. So this study also shows the efficiency is much enhanced. As you can see, the average is about 7.1, but you can see you can reach up to 10 there during the morning hours as the overall system efficiency. Therefore, this study has much. So you can see the solar radiation of the design month June there as the design month with the least radiation in Lesotho for our dosing area, and also the monthly output and of different pipes. As you can see, the June month having 350 millimeter cubic meters daily as an output, as a prediction. And also you can see that November and December months have the highest water delivered from all the pipes. And from there, we can design a storage by using a static shrinking model of temporal and distribution, which takes into account the surplus and the deficit of the demand and supply, and you add them, then you can find the balance of storage, which differs from the traditional method, which just takes into account of 350 cubic meters daily demand, and then you multiply by autonomy days. This balance of storage minimizes the cost, hence, since it's lower when you multiply 255 by autonomy days. Those are our dark days. And from there, we can see our cost of pumping analysis. You can see that the 140 millimeter pipe can be our rational pipe, as it has the least cost of pumping, and also the 200 millimeter pipe has the highest unit of cost of pumping. However, we've reduced required PV. So it should be noted that the pipe's diameter and the PV makes the rational decision in this analysis. So the 140 millimeter pipe in this case study was the rational choice. As you can see in our conclusions there, the traditional methods will size the TDH as 79 due to having a single duty point of peak sunshine hour. Therefore, you will have a very much increased TDH for that required water. And also, you can see that the PV is much reduced. This study shows that the feasibility of these pumping systems relies on the modeling that is with time-step variation of solar radiation. That takes into account the time-step variation of solar radiation, not only the single duty point of traditional methods or the grid-based methods. So from there, the study recommend that the Department of Rural Water Supply and Department of Energy specifically adopt this model for reliable and efficient implementation of electrified rural water projects. Also, as part of recommendation, computer programming can be used to upgrade this model to software application for automated, easier application. I thank you.
The first question is, your graph seems to be having very few data points. Can you discuss why this is the case? I guess it's this one. I think you go forward. I guess the person is asking is talking about this graph.
It has very few data points. That is the axis down there. The x-axis is not. Oh, it is because we sampled only 4 standard pipes. The 125 millimeter, the 110, the 140 millimeter, and 160 and 200. As they are the standard pipes that could deliver, as we assumed, for 1 meters per second velocity. So those were rationally, it is an engineering intuition to understand that we will not need more than 200 millimeter or less than 125 to deliver water for. That's why we sampled only 4 pipes, because we knew that
the data points are not about the pipes, are they? I mean, the colors are different pipes, so it's like 2 pipes or not?
No, it's unit of cost of pumping. It's analyzed by the color red and the required PV by the color blue. So the first point is 125 millimeter point. You can see that it requires 225,000 PV, and the cost of pumping is less than 4 US cents, as you can see. And also the 140.
I think we get it. So each point is a pipe.
Each point is a pipe.
Okay.
So it shows that as the PV reduces, when you increase the pipe, however, the cost of pumping increases. As you increase the pipe diameter, the PV required to deliver water reduces. As there is less friction.
Next question. Is the data through simulation because the graphs showing results?
Yeah, they were simulated by the Hove model.
Okay. You conclude by saying that computer programming could help. Could you explain its advantages and disadvantages?
We can comprehensively take all the equations that govern this model and also the economics and put them into one ease of use so that it can be easier used. So that you just put the inputs and then you analyze using single model and single software. just like other softwares that could be used, like PV system, which we ignored because they could not take into account technical, economic, and water demand and the climate into one model. So we will need a model that can do that comprehensively, like this model did.
Yes. So you said the results, you obtained the results through simulation, isn't it? That you have.
Yeah, and as you go back, other results were done. These results of radiation maps were derived from PVIGS, GIS, so that we retrieve data of 10 years from PVGIS. So these results of the illustration of temperature were from the PVGIS.
Okay, that. Thank you. Please unshare, and Telkhanya, please share your screen. You have shared the desktop. You haven't shared the file that you're presenting.
Yeah. Okay. So is it shared now?
No, not unless it's loading. So go to the first slide and start.
What could be? Let's open share screen. Share. Screen is sharing. Yes, that's what it's saying.
What happened? You had the file opened.
I have the file open. It is just written. Screen is.
Nothing is seen but the desktop.
Oh, now.
When you press the share option, you should click on the window of the actual presentation itself.
So slideshow.
Even now.
Okay.
Yeah, we have it now, but make it a slideshow.
Okay, thank you very much. Okay.
Sure.
Can I start?
Yes, please.
Good evening, everyone. Is Letseng-la-Letsie. I'm presenting analysis of Letseng-la-Letsie River for hydropotential. My speakers are Dr. Khaba and Dr. M. Machele. The country have got a power deficit in the sense that we are only able to generate about 66% of the power we use, and other 44% is being imported from neighboring countries according to 2019 studies. And this power deficit is more prominent in rural areas like Quthing. Therefore, those rivers, the rivers within those rural areas to be assessed with the main objective to inform makers that the hydropower plant in those areas can be developed, and also in the objective of attracting investors such that they can invest on developing hydropowers, and ultimately indirectly to increase electricity in those areas. Now, background, Quthing River and Letseng-la-Letsie are situated in the southern part of Lesotho, and the catchments here are good and attractive power potential. But the only problem is that around those where hydropower is potential. There are no flow rays like these places, in these places. The place is far away from them at the end of Quthing River somewhere. But with the establishments of catchment areas like catchment area of River and the catchment area of Quthing and the catchment area of Letseng-la-Letsie, those flow rates can be derived. Our methodology. The most important input parameters for hydropower potential are flow rates and head. To determine head, the digital map chart and the contours were generated from the contours. Course head was computed. From course, some losses subtracted and the net head was determined. To determine the flow rates from Department of Water Affairs, processed such that applied area ratio such that I can get the flow rates at engaged stations where I have the potential to generate power. From there, I developed hydrographs. Since it is not that in hydro developments, I just showed the box for flow duration more important. From flow duration curve, then the design flow determined. With the design of determined, the net head determined, the hydraulic power can be computed, and from hydraulic power, the mechanical power can be computed using turbine, and I have used Turbine Pro, and then the electrical power can be computed. Now the files are the one of flow duration curves between the flow rates from DWA. Flow duration curves are useful for determining the design. Looking at below, we have got flow rates in sub and then see a subcatchment. From Quthing catchment, we design flow rate. Two of them, the rate selected at 60 percentile due to use of electricity in rural. And for Quthing area, 0.58 meters cubed per second, and then for analysis is 0.11 meters cubed second. After determining the flow rates, the next step is to determine the head. And to determine this, with the powerhouse at this, which is about 1840, and the head losses of 10.7 meters, the net head will be 153 to 3 meters. This was determined using this digital elevation map concept. And the same was also applied for determining the head for Letseng-la-Letsie. Now with the head and flow rate determined for both catchments, the next thing that can be determined is the hydraulic power. So applying this typical formula or the common formula, the hydraulic for Quthing River is 906 kilowatts, and for Letseng-la-Letsie 246, which is shown by this red graph here, and for Letseng-la-Letsie is shown by this. Now the next step will be to determine the mechanical power. Looking at our net head and flow rates, can be seen that the head are high and the flow rates are very low. So from turbine graph, the turbine that can feature well there is a Quthing turbine. So using the Quthing turbine, typical efficiency of 90% from literature, the calculation gives me that shows that if I apply 20% to this hydraulic power, then the output of the Quthing turbine will be 815 kilowatts for typical performance. With the turbine pro model, it also shows 58 meters cubed, the output power is 815 kilowatt, and it also that this can be added over even more power, but is not actually encouraged. This will be the power out of the turbine be installed. Now the same concept can be applied to Letseng-la-Letsie, and the output power from the built-in turbine there will be 221 kilowatt. Now the next step will be to determine the electrical power, but before you go there, we can see the mechanical power on Quthing River is high, and therefore a bigger turbine will be used, and this one will have gas and will be vertically oriented. For Letseng-la-Letsie is small, and then the smaller turbine with two gas will, and it is horizontally oriented. Now, applying the typical generator efficiency of 99%, generators are considered as lossless equipment. The output of the generator at Quthing will be 80 kilowatts, and from Letseng-la-Letsie 219 kilowatts. Now, the energy that can be harnessed from Letseng-la-Letsie using the capacity factor of 0.46 from EIA, which says it is the typical capacity factor for Africa. Applying this capacity factor or this generator output, energy that there is 3.46 megawatts, and the energy that can be harnessed from Letseng-la-Letsie is 0.95 megawatt. Now, in conclusion, can say there is potential of hydropower from Quthing River and Letseng-la-Letsie. This analysis will be availed to policymakers for hydropower development. It can also be availed to independent producers who can invest in hydropowers. Recommendations, can say field assessment be conducted. Overall, the overall study was made in the reconnaissance level, where most of the values were not the like the rates were actually extrapolated using and ratio, and surveying also is needed that we can come with ground data. Economical analysis is also lacking. Thank you very much for your time.
Thank you, Tate Lukhanyo. First question, what does EIA mean about a typical capacity factor for Africa? What does that mean? Should it not be a technology-related factor?
Okay, I through the hydropower graphs in the literature, and then they were actually comparing them, the ones in Asia, the ones in Africa, and then I got this this one from that EIA study that were conducted.
There's a follow-up question, and please unshare your screen, and Mukeke, please put your screen.
Okay.
Can you not calculate capacity factor from available data rather than an assumed factor from the internet?
That would need me to get the demand.
That would be?
The power supply. And the load demand was not actually easy to, because analysis is being done on as the what way of trying to curb power deficit. So it was not easy to the capacity at time.
I didn't get your answer. Not
That's why I'm saying yes.
Are you saying there is no data for you to do calculations?
For the calculation, it is there, but only the flow rates, and but for the no specific what specific load targeted, but it was done as to curb the deficit. So
maybe we should go to the next question.
Okay.
What was the rationale behind choosing the 60% exceedance value for Q?
The rationale is rural area people, they are actually using electricity for about 20% of the time. So I didn't want to use the design flow there. I was catering for scalability that as time goes on, they will use electricity most of the time. So I choose it at 60%.
Was the data used for the study assumed or empirical?
The data, I got it from some of the literature.
The data for Quthing, you got it from the literature?
Yes.
Which literature?
BOS.
Okay.
Yes. Yeah.
There are more questions. Please address them in the chat room. Mkeke, please go ahead. But Mkeke, you might have muted yourself. You might be talking to yourself.
He's still on mute.
So can you hear me now?
Yes.
Okay, I'm saying I am Subata Mkeke and I'm presenting to you the project entitled The Impact of Intermittent Renewable Energy Generators on the Lesotho National Grid and supervised by Ntate. I seem to be okay. So this will be the contents for the presentation. I will cover the introduction, methodology, results, conclusion, and then who are benefiting from the study. And then why should we integrate the renewables into the grid? It is because Lesotho has a very low electricity access, and also the generation has been stagnant. Also, the increase in load demand in Lesotho is met from the imports, which compromises the energy security for Lesotho. Also in Lesotho, electricity access is mainly done through the grid extension, which calls for large power utility scale power plants to be built. But Lesotho does not have any fossil fuels to build the power plants from it. Hence, it has to rely on its renewable energy generators. And in that regard, there have been some studies to assess how much renewables, how much power could be generated from renewables. And then it was found that for the wind, from the study from LEC in 2010, for wind, it is estimated Lesotho can have 758, and then also for the solar, it was estimated by Taylor et al. That 5.5 and to 7.2 radiation could be good for large utility scale power plants for renewables. And also Lesotho in its action agenda plan, which is to meet its growing demand through the renewables. But the problem with renewables is their variability and uncertainty, and that results into the grid stability. Hence, the objective of this study. The objective of this study is to assess the impact of intermittent renewable energy grid into the impact of intermittent renewable energy generators on grid stability, and then determine the maximum allowable penetration for the renewables. Also to assess the steady-state voltage stability. The emphasis will be on the frequency, voltage, and the rotor angle stability. The two places considered will be Letseng and Hydropower. And then how is this going to be done? The approach to do this was to consider both the steady-state conditions and then the dynamic conditions. For the steady-state, the load flow, the hourly load flow was conducted, and then the voltage variations were monitored as the renewables vary under different penetration levels. And then for the dynamic simulation, what was done, a fault was applied at a certain point, and then observe the responses for rotor angle frequency and the voltage. And then if the stability is observed after applying the fault, the penetrations are increased up until the stability limits are violated. The tables here show the voltage limits and the frequency limit as prescribed in the grid code of Lesotho. These were the formulas used to calculate the power from wind and solar. And then the first table here shows the table for the critical clearing times. As I have said, that for the dynamic simulations, we will have to find that point. And that point was found to be Mabote, since it has the lowest critical clearing time. And then what follows could be based on the then what will follow is what will happen. We will now look at the responses of both frequency and the voltage and the rotor angle as the penetrations level. This graph considers the voltage response when the fault is applied at Mabote, and then try to see if the system, how will the system behave as the penetration increases. It is observed that under the 20 megawatts solar penetration and 30 megawatts solar penetrations, the voltage stability was observed, but for the 36 megawatt solar penetration, the voltage stability limits were violated. The same thing could be said for the frequency responses, where as the penetrations increased up to 36, the frequency stability limits were violated. For the rotor angle, what could be noticed is that as the penetrations increased, the rotor angle swings also increased. But it should be observed that for the penetrations of 30 and 20, even though the rotor angles was swinging, but it was swinging within the stable limits, hence the constant power. And then for the wind case, the same thing was done to see how the voltage, frequency, and the rotor angle will respond as the wind penetrations increase. For the wind case, it is seen that as the penetrations increased, the voltage at the point of common coupling, that is where the wind, the wind power is integrated to the grid, it's increasing. And notably so at the nearby substation at Quthing. And then as the penetrations level increased up to 52 megawatts, the voltage at Quthing exceeded the prescribed limits. Hence, that simply suggests that we cannot go beyond 52 megawatts. For the frequency, it is observed that the frequency was always after the fault, it was always dumped to the stable limits. And then for the rotor angle, it is seen that as the wind power penetration increases, the rotor angle swings didn't increase. And then the other case, which was trying to hybridize both wind and solar, and then try to see if maybe hybridizing wind and solar will result maybe into increased penetrations of either. But the results reveal that no, in that case, the very same limits which were calculated under solar only and wind only remain the same penetrations. And then for the steady state voltage stability, the first point which were considered were the point at the point of common coupling for both Letseng and Hamahoto. From the red graph there, it shows the voltages at Letseng. It is shown that Letseng, the voltage there varies drastically, but it varies within the prescribed limits of 10%. And then for the other buses which were considered to be critical, Muyela and Mabote, it is seen that the voltage always oscillated within the prescribed limits. And then the other points which were considered were the neighboring substations to both Mabote and Letseng. Under those conditions, it was seen that the substation that nearer to the solar plant never experienced any voltage stability issues. But for that, in the wind, the Letseng substation again, there shows that at high wind generation, the voltage can exceed the prescribed limits. And then the conclusions. From the simulated results, voltage, frequency, and rotor angle stability worsens as the penetrations increased. It is concluded that for solar PV, the maximum that could be integrated at Ramarotole could be 35 megawatts, and then for wind at Letseng it could be 50 megawatts, and then the steady state there at Letseng should there should be in order to cater for the 50 megawatts penetration. That simply says that there should be some control strategies to make sure that the penetrations at Quthing are not exceeded. And then for further studies, I think it could be nicer to also assess the power quality and harmonics, and then also try to assess how the protection system will perform under the renewables. And lastly, I think it is important to always assess the cost of this integrating these renewables. And then who will benefit from this study? Mainly under the electrical energy
So the first question, I think Almas has a comment about your units not being consistent. The first question is, what is the impact on the voltage and other parameters of having the renewable energy generators constructed at many locations instead of one? Certainly this should have significant effect, probably to increase the renewable energy penetration thresholds for the Lesotho. So the impact of connecting at many places?
The impact of connecting, like trying to test like many places around Lesotho.
Yeah, the impact of having, say, solar farms and wind farms scattered throughout the country, because what we have talked about here, it's only connection to one point, right?
Yes, I do get the question, and for many places, I think I did not do the cost. At those many places, it will depend on the both solar and wind resource. So it cannot just be put anywhere like many places. It should be put depending on the resource, and these places were considered because they have good solar and wind resource. So I think we should consider the most places, the places which will yield the most power, not just like any place.
Yeah, but I think the question is, what is the impact on the grid of connecting from many places? As as opposed to connecting at one place. The impact on the grid, not the resources.
Yeah.
On the grid, if you connect from a lot of places, as opposed to connecting from one place.
Okay, let me maybe try to get the question again. Maybe still connecting at the transmission level.
Yes.
Yes.
At different places.
Yeah.
My question is, if you put all the resource at one place, then obviously the impacts on these parameters will be more than if you put smaller resources scattered all over. The effects might be cancelling rather than going in one direction.
Okay. I think I do now get the answer. I think the answer is because at transmission level you cannot be putting like small generators. You need to put big. But maybe when you go to for small generation units, then you go to the generation the distribution network. And then for this study, I did not consider for like small power plants. I was trying to consider for utility scale.
Yeah, but
not necessarily
I think you're not getting the Tawanda, give me a chance. I think you're missing the point. The point is having those many but huge generations, but scattered instead of putting them in one place. But I think we need to move on to the next question, please, and share and let the next person share his slides while I read you the next question.
Okay.
From the assumption that you will need even more renewable energy system penetration than the maximum you calculated, what levers does the grid operator have to allow more renewable energy systems?
May you please come again? I did not quite get the question.
Starting from the assumption that you will need even more renewable energy systems penetration than the maximum you calculated, what does the grid operator have to allow for more renewable energy systems?
Okay, thank you for the answer. I think I do get the question, but you will also guide me if I've not answered quite well. Basically, if you need to allow more renewables into the grid, that would mean that the network needs to be more flexible, which means the network will have to be fortified. And then that would mean that the network should be upgraded. And then also, since the variability now will start to have more impact, that would mean you will have to have like more of these other units, which the balancing units, which means like those things. But in all, what that means, that simply says that you will need more sophisticated network, and then you will need the balancing strategy just to make sure that the grid operates at still at a normal reliability.
Yeah, okay. There are more questions for you in the chat room. Please respond to them. Tate Mulolo, please go ahead.
Thank you very much, Nadempolo. I hope everyone can hear me.
Yes, we can.
Okay, thank you. My name is Tsepa Mulolo, and I'll be presenting to you the project entitled Energy Supply Management System for Lesotho, which is a user interactive system. I'm being supervised by Professor Zektamai. The agenda for this presentation, we'll discuss the introduction and some background and the methodology, results and analysis of the results. Then we'll have some recommendations and conclusion. And what we can say is that for each and every country, including Lesotho, to be very particular and observant about its energy situation, it should adopt an accounting framework around the energy sector. This involves knowledge about its energy supply, energy flow in the economy, and also energy final use by different economic sectors. So to achieve this, actually, this accounting framework, energy products data should be adequately collected and stored on regular basis so that it can be accessed anytime. So Lesotho, however, has a challenge of energy products data availability due to deficiency in data collection in its energy sector. And this makes it difficult for the sector to embark on developing the energy accounting framework, such that its energy status could be visible to every stakeholder in the country. It further hinders future decisions to be made on the energy situation, such as the security of supply, self-reliance, renewable energy sources penetration, as well as management of the greenhouse gas emissions to the environment. So we proposed a solution to this problem. We said maybe this is due to lack of tools that could be used to capture and store the energy data. So we propose to develop a user interactive web-based energy supply management system. And also into that system, we input the available data for Lesotho. And we source data from the Department of Energy Statistics in the Bureau of Statistics for 2017 and 2018. And then we analyze Lesotho's energy situation using such data in supply just to show how much this system can be useful to the country. So this system has been developed, has been divided into 3 modules. The user interface, where the data will be inputted from by the users, then the data processing, as well as the database where the storage of the data will be there. And of course, all these things will be interrelated. And of course, the data flow will be all the way from the user input to the database. And of course, it can also be retrieved from the database directly to the user interface to be used in whatever way it can be used. Now, the methodology approach that was used in this was to build a system following what you call the continuous delivery or continuous development. First of all, we designed the system. The user interface was implemented using the hypertext markup language. And the functionality of that system, we employed the personal homepage program or the PHP, and in the database for database management, we employed the structured query language. And after that, the platform that was used to deploy this was the Visual Studio Code on the Laravel framework. And of course, as I have earlier alluded, that as system input, we used the 2017 and 2018 data that was sourced from the Department of Statistics, Department of Energy Statistics. And of course, from this, the system output would be the energy commodity account for the country for those years, and the energy balance for those years, as well as the aggregated data that we can just query from the system for any particular type of energy data product you want to see for a certain period. And from there, the system was released and hosted on the cPanel hosting platform. So, and of course, this system could be accessed for those who want to access it. They can access it over this website that is shown there as the system demo. So when you get into the system user interface will look like this. You will have a tab where you can be able to register your name so that at least you are registered into the system for you to be able to log on to the system using those registered credentials. Then from there, once you are into the system can be, the functionality of the system, you can input data, energy product name is the first thing that we can input into the system. You can see that for Lesotho, we have those kind of energy products that are used in the country, the biomass, coal, electricity, LPG, petroleum, and renewables. The second aspect is for you to input the product source as to whether the product name that you are inputting, where does it come from? Does it come from production? Does it come as an import, or is it an export, or does it come from stock exchange? And finally, you'll have to input the quantity of that data as well as the date the date of that input. And of course, as you input them, all those information, such information will be directly stored into the database. And of course, the system outputs at this stage will be the energy commodity account. And the snapshot that I've shown here is for the year 2017, whereby now all these energy products are shown in their physical units. You can see that the biomass is in tons, coal products are in tons as well, but the electricity is in megawatt hour, and so on and so forth, as you can see from there. The other important output of the system will be the energy balance, whereby now those values from the energy commodity account now will be converted to a common energy unit called, in this case, the kiloton of oil equivalent. And for this one, it's for the year 2017. Whereby you can see now all these parameters here now, all these energy products are now shown in this report in the common energy unit. And from there, you can also aggregate data, depending on what kind of data, if you want to know the amount of biomass that was produced between a certain day to a certain day, you can filter out that and get that result from there. And you can even download it, export it to your machine in whatever form you want, maybe in PDF or in CSV format or Excel format. Now, from this data that we used for the 2017, we were able to provide analysis of the results that were obtained from that report that was generated from the system. We were able to analyze Lesotho's energy supply mix. And of course, from this graph, we can see that biomass seems to be dominating the supply, followed by the petroleum products, which means in this case, we can say if petroleum products are significant down, we can say Lesotho still has some contribution to the greenhouse gas emissions. And of course, from here, we can see that the renewables in the supply of energy in Lesotho are not featuring from this analysis. From there, we also analyzed Lesotho's energy self-reliance for the year 2017. And then we could see that 75% of the energy supply comes from production. And of course, this production is covered mainly by the biomass, which is used mainly inefficiently and unsustainably by the majority of the population in Lesotho. And the 25% is the energy that could be used, maybe comes from the electricity, as well as the petroleum products and coal and of course the LP gas. So from this, we could make some recommendation that this system has to cover all levels of the energy flow, from the supply to the transformation, all the way to the final energy used by different economic sectors. Right now, this system only concentrated on the energy supply of the country. And of course, the other recommendation would be that the energy data collection should be legislated to enforce data collection in the country, because this is already happening in other countries such as Europe, whereby the energy data is being enforced to collect it. And this could be passed through the energy policies, as well as we should have the renewable energy technology exploration to enhance security of supply in the country, and also to close the data gaps in most energy sources in the country. So we can say that this energy supply management system achieves the desired goal of data capturing and storage. And of course, we can say that for the literature gaps, the existing studies related to systems of this nature have paid much attention to the use of energy data at consumption level, whereby a system would capture data consumed by different sectors.
Okay,
thank you, Ndari.
Question. Is the system responsive? Can I access it using a mobile device? How usable
Yes,
is the device? How secure is it from cyber attacks?
One of the limitations that I just wanted to impose is that this system is not that robust, but it is secure, because
So can it be accessed using a mobile device?
Yes, can access it right now if you can.
Okay. Please
Yes,
screen and Ndate share your screen. There are still a couple of questions for you in that demo. So biomass is not classified as renewable?
In Lesotho, it's not, we cannot say it's renewable because we are just cutting down the trees and then they are not being replaced.
Okay. So
yeah,
he now knows that his cost is not renewable. Okay. Another question says, we have in Lesotho a lot of production coming from hydro. Why is it not featuring in your result pie chart?
the hydro is captured under the electricity, production of electricity there.
Okay.
Yes.
Another question says, should data sharing be in line with open data framework?
I think yes, we can have data sharing on the open data framework.
Okay.
As long as it's legislated, I think it can be controlled in any way.
Okay. There's still
yes.
more questions for you in the chat room, so please join in there. Ndate, please do a slideshow. And we should agree with you that should you have technical issues, you will unshare. We are not going to shut down again and come back. You will unshare your slides because we think the problem is coming from your slides.
Okay, in that.
Data slideshow, please. Sure.
So my name is Bulani. I'm going to give a presentation on the development of solar radiation database and its integration into solar process application in Lesotho. I'm supervised by Ndate Tawanda Hobe. This study spans a region between longitude 27 degrees east and 29.5 degrees, and the latitudes between 28.5 degrees south and 30.75 degrees south. There are only 7 solar radiation mission stations in Lesotho, which is a problem. There are also few published solar radiation database in Lesotho, only 12 stations published by Quthing in 1988. There is a need for standardizing estimation of solar radiation between stations for proper implementation of solar projects, as well as there is a need to develop accurate database by merging ground measured data with satellite measured data, and then calibrate it with solar radiation derived data. This study is based on clearness indices for both ground and satellite measured data as per these equations, where K ground is monthly mean ground clearness index, K satellite is monthly mean satellite clearness index, and H ground is monthly mean ground solar radiation, and H naught is monthly mean extraterrestrial solar radiation. This study is based on the correlation functions, which relates ground measured data and satellite measured data. And they are developed such that this equation is satisfied, where D and E are site-specific coefficients and they are constants. The coefficients D and E, they form the basis for calibrating continuous satellite measured data to ground measured data, such that this relation is being satisfied. As well as, then after that one, then we develop an interpolating tool which read and interpolate data anywhere in Lesotho into solar application process. The detailed methodology of the study, first of all, we plot the coefficients D and E for all 17 stations. Then we divide the country into grid points which are over 5,000. And then using server software, we map coefficients of all 17 stations And then we read and record coefficients at each grid point. Then after that, we validate the coefficients using a leave one out cross validation. Then after validating, we apply this, we establish the solar radiation database for Lesotho by applying this equation. Then after establishing the database, then we test the accuracy of the database by using statistical tests. First of all, we find relative bias error using this equation, where data known is the value of the known data sample. Data estimate is the value of data sample being investigated. After that, we find relative mean bias error using this equation, where data known is the ith measured known data set. Say for this, for in particular, we may say month. The data estimate I is the ith estimate of a known data set. Then we find the relative mean square error using this equation. Then after finding that one, we find the normalized root mean square error using this equation. From the results of the study, we realize that there is a strong correlation between ground and satellite clearness indices, as shown by this sample graphs, which was at Quthing and at Maseru. Here we are having an extract of a developed solar radiation database for Lesotho. This database, it covers the whole country. This is just an extract, all as per those grid points. It was developed using this equation here. Here, then, like we said in the methodology, that we need to test the reliability of the database. We find that between January and June, the database accuracy is between 1.1% and 1.9% between January and June. And between July and December, we find that the database error is between 1.2% and 2.7%. Here, we are having an annual mean solar radiation map for Lesotho, which indicates that the western part of the country, that is the lowlands, have higher radiation values as compared to the highlands areas. And in particular, you can see that the southwestern areas, like those areas of Quthing and Mahalisuk, they have a higher radiation values. And then we can see along the Senku Valley here, we're having a bit higher solar radiation. And this graph shows that the improved database, it has a similar behavior as the established database. Like we can remember that in the introduction, we say that the database, there is a database which was introduced by Gopinathan, and then there is a database which was obtained from measured data. The satellite, and then there is a database which was obtained from the satellite derived data, which is shown by a green color, and then the Gopinathan database is shown by the red color, and the improved database is shown by the blue color. And then, like we said, that there is an interpolation tool that has been developed. From the improved database in December, at particular longitude, at this longitude, 28.5 degrees south and 27.55 degrees east, mean solar radiation is found to be 7.47. And using the interpolation tool, the results, we get the result as 7.504362 kilowatt hour per square meter. Then this shows that we can say that the error of the interpolation tool in reading the database is just under 1%. It is 0.46%. So we can say that this tool is more is reliable. Then in conclusion, we can say that from the study, the statistical tests have established that new solar radiation database for Lesotho has a maximum error of 2.7, which occurs between July and December, and a minimum reliability of 97.3%. And this study has established interpolation tool which has a reliability of 99.54%. And again, we can say from this study has narrowed the gap on spatial temporal distribution of ground solar radiation knowledge in Lesotho by merging sunshine data, ground measured data, and satellite data. The study has also built a molecular solar radiation database for Lesotho, thereby easing building of accurate renewable energy policies, in particular in relation to solar. The study has also established a reliable method for estimating solar radiation at any location in the country, thereby ensuring proper techno-economical assessing of solar application projects. Then these are the references which were used to construct the presentation. With this, I thank you all.
And we are thankful that the gods were on our side. We've been holding our breaths. Any questions for Ndate Bulani? Have you tested the government's ability and appetite to take this tool up?
Actually, I have had a talk with the Department of Energy, and then actually I can say that the person that I met, he was just about to meet with the director of Department of Energy, and I believe that is going to take it.
Okay. Any other question? For Ndate Bulani? Did you just use 1 point for testing in order to get the 0.46%?
For the interpolation tool, or for which point, sir?
I'm not sure. Please scroll through your slides. Let's see where the 0.46% comes from.
Or this one? Okay, for this particular one, the results are the same, because in the document, in the report itself, a number of points have been used. The results are the same, but for presentation's sake, I just picked only 1 point.
Any other question for Ndate Bulani? What is the relationship of the data needs to exist in databases like Global Solar Atlas?
Actually, I can say that is more or less the same, because the Global Solar Atlas is basically based on satellite derived data, and our data has merged ground measured data as well as the satellite data. So I can say that the relationship is pretty good.
So you're the last person, so you may have all the questions. So I'll open the floor for comments and suggestions and recommendations and your observations from this presentations, and also from browsing the dissertations if you did. I must apologize that I have an obsessive compulsive disorder with regard to time. So people who work with me would know that, so please bear with me. But I mean, we just overran now only because we had a problem in the morning, but otherwise we have finished on time, which is critical for me. So any inputs from the floor so that we do it better next time? This is our first cohort of our MSc in sustainable energy. So any inputs would be very helpful for us to structure a better program.
May I say something in that, Mpolo?
Yes.
You hearing me?
Yes, Dr. McDiv.
Okay, thank you very much. This is a kind of general comment now I am saying. In the first place, I would like to congratulate
I don't know if I'm the only person who can hear you.
fruits from our program, ERC. In fact, we know that energy is vital for survival and development. So in order to fulfill the energy requirements of the country and beyond, I am commending all the graduates to participate and bring and do the best gear as possible to bring development for the nation, to use all the resources what we have in Lesotho. As indicated by the last one, or maybe the second from the last presenter, the bioenergy resources as a feedstock, more than 75% of the resource we have here, we can use it in the integrated form with other renewable energy sources. And then my advice to you, graduates, now I say graduates because you defended and presented and built the capacity. So thank you very much. And then I really felt great for what you have done. Thank you very much.
Thank you, Dr. McBeeve.
Good.
Any other person?
Yes, may I?
Yes.
All right. To all the presenters, and I reiterate to the previous speakers' comments. Congrats on all the hard work, and I'm definitely on the same boat with you. Yahore, energy is a very, very, very important driving factor for growth. And as a result of that, and from the feel and the taste of the presentations given today, they are, in a very good way, not purely academic. So there's a practical consideration to all the research topics, which I really appreciate. And then at the same time, because of the practical nature of the work that you guys have done and the findings that you have come up with, the one recommendation I would make is that when you then present the findings of these kinds of works, you have to take the extra measure or the extra step to do what we can call a real life analysis, which is to say, now that I have found this information or I have developed this insight, in a practical way, how does it get implemented? I'll just make an example with the run-of-river hydropower analysis done for, I think, in Lesotho. You know, once you have found that you can reduce diesel costs and other costs, then the next step is to say, what is the financial savings and what do I need? What is the capital requirement for the intervention I have suggested? And therefore, does the business case make sense? So you almost have to tie it up so that if it is a practical recommendation you're making, the person you're making it to has a complete picture and can easier make a decision. Whereas if we leave it at the step that it is now, you know, the person can say, okay, this sounds good, but now more work still has to be done for me to make a final decision. So that is almost the responsibility of this kind of work. But otherwise, I really enjoyed it, and congrats to everyone.
Thank you, Dr. Malova. More comments, especially not from ERC, from people from outside, so that you help build us. Almas, Chris, Jacob, Yoni.
Yes, I'm impressed. I'm glad I had the chance to follow this. I'm very glad. I can see that young people are working on the energy problem in Lesotho as well, and taking energy very serious. It's all over the world that we have to work on renewable and sustainable energy. And Lesotho is the luck, I must say, that it can go 100%. It was 100% renewable electricity. Now it's at 50%. It can go back to 100%, and to the benefit of the country and the world even. So you do great things by studying all aspects of energy, and please keep going to make it work. There are lots of opportunities, very interesting things to do. I would encourage you to go further with this. Thank you.
Thank you, Chris. I realized Niklas joined a little late. So Yoni, Niklas should talk after you. I mean, Niklas helped us build this program, so he should say something as much as he only joined the last presentation, I think. And Yoni helped us a lot too.
Yeah, this is Yoni. Congratulations to everyone on your interesting work and interesting presentations. Just wanted to thank for the opportunity to follow and be part of seeing some of the results. I guess I would just like to say that remember that you now have the most cutting edge knowledge on the topics that you have chosen and worked on, much better knowledge than many others. So I wish you all the best in using that knowledge and extending and deepening it further. And I hope to see you again soon.
Thank you, Yoni. Niklas. I guess he doesn't want to talk. That's fine.
Plus, mic is not connected.
I see. So maybe he's not fully connected. I don't know. Any last words from anybody? No. Then I'll send the data as the dean. You say something.
I don't have any words that I'm follow.
Maybe quickly, Ruketsi,
yes.
Thank you for the presentations. I only was able to follow in the afternoon, but I joined the comments by others made. Thank you for them. They were very interesting pieces in that pieces of knowledge, and I was thinking, what can I remind me of my time when after I graduated. I wish you can find an encouraging, challenging environment, working environment where you can grow and take the expertise that you built up and will further build up to real life solutions. So I'm wishing you all of that. Thank you and good luck. Yeah.
Thank you, Jacob. Okay, so let me thank all the students for the hard work and for having to suffer dealing with our constant demands and deadlines. I'm sure it wasn't easy, but I guess you now realize it was worth it, I hope. And thank you to all the participants in this call. I know most of you had to leave. Important work that you need to do and join us and help us build this program. We are really thankful. And we hope we'll still get your support moving forward over and above, attending these meetings, but helping us in many other ways to build a better program and address the challenges, the energy challenges of Lesotho and the region. We really thank you for your time and patience and support. With that, I'll say thank you, everybody. Let's go have a drink or whatever you need to wind down.
Yeah, that's
we'll all
great.
go for a run.
Yeah, this is the new normal. The new normal, COVID crisis is an opportunity, in fact, to deliver throughout the world. So this is a good opportunity that we heard in Europe, in Africa, in America, wherever. But the unfortunate part of this is that we can't really be together to toast for the best work what our students did. Anyway, congratulations, Riva.
Bye, everybody. So Nicholas decided to connect while we are leaving. So bye-bye.